All right. Hey, Honors Chemistry. I wanted to do one more question from worksheet number 4. So I want to do number 3. And so I'm expecting you to finish this worksheet, and we've done at least 3 of the problems on here to get you going. So I'm hoping that these videos can kind of help you finish the problems on the back so you know what you're doing. All right, so let's look at number 3. A 12-ounce can of soft drink, assume M is equal to 350 grams, so they give you a mass, at 25 degrees Celsius is placed in a freezer where the temperature is negative 12 degrees Celsius. How much energy must be removed from the soft drink for it to reach this temperature? All right, so it sounds like I'm doing something kinda opposite from my previous video in question number 1. If you recap question number 1, I heated up I actually melted something and then heated it up beyond that melting temperature. Now I'm gonna cool down something and try and freeze it beyond that temperature. So there's a couple of things that are gonna be going on in question number 3. This is a couple of steps here. All right, so here is my time, seconds, which is also my heat as it goes on. All right, and here's my temperature in degrees Celsius. So we have to be careful because there's going to be a couple of segments here. So I start out at 25 degrees Celsius. All right, so I'm up here at 25 degrees Celsius. I start out there and I have 340 grams of it. So I start out at 25 degrees Celsius, and what do I have to do to it first in order to freeze it? Because if I put this can of soft drink in the freezer, it's not going to automatically freeze. What has to happen to it first? Think about what I've been asking all of you about boiling water. If I have water on a pot, does it automatically boil? No, I have to heat it up first. So similarly, what do I have to do with this soft drink before it freezes? I have to cool it down. And what temperature am I going to cool it down to? I'm hoping you're saying 0 degrees Celsius, because that would be the freezing point, assuming it's like water. So most of the things that we drink in this world have 70 to 80% water with some crap mixed into it. So it's mostly water. So 0 degrees Celsius is going to be that freezing point. So I have to bring it down from 25 to 0. Then I freeze it. So I have my liquid and it's cooling. And in this process, cooling means it's losing energy to the surroundings. All right, and this is in a refrigerator. And remember, if energy is being lost in the refrigerator, and we jokingly called a freezer or refrigerator a heat remover. That's really what a refrigerator is. It removes heat, and that's why if you put your foot or your hand underneath the refrigerator, it's warm because it's removing heat from inside. So I'm removing heat from this liquid, and then it's freezing, and I'm removing more energy, so it's losing more energy. Now, I wanted to go from freezing to negative 12 degrees Celsius. How can I get the soft drink to go to freezing to reach this temperature of negative 12 degrees Celsius? So now what do I have to do? I have to go from 0 degrees Celsius down to negative 12 degrees Celsius. So there are 3 segments here. And for however many segments there are, that's how much energy calculations I have to make. So I have 1, 2, 3. I'm going to do 1, 2, 3. And then just like in my previous video, once I get this energy, I'm going to add them up and say that's how much energy I need to remove, or that's the energy negative. So in segment 1, I want to cool my temperature. I want to go from 25 degrees Celsius to 0 degrees Celsius. So my delta T is equal to negative 25 degrees Celsius. If I change my temperature, what equation do I use? What equation do I use if I change my temperature? Well, I'm hoping we would say, I need to use Q equals MC delta T. This equation is related to anything having to do with temperature changes. My mass was said to be 340 grams. We are at a liquid, so my liquid water or my liquid substance has a specific heat capacity of 4.18 joules per grams degree Celsius, and my delta T is negative 25 degrees Celsius. If I do this math, I'll do negative 25 times 4.18 times 340, and I get negative 35,530. So my Q is equal to negative 35,530 joules. Degrees Celsius cancels out, grams cancels out. Now, why is this negative? Negative because it is cooling. And that means it's losing energy. And the energy is going to the surroundings. To the surroundings. Just in case we need to keep that definition in. Okay? So now I have one value here. I'm going to call this for segment 1. Let me do 2. What am I at now? Well, I have to freeze this liquid. If I want to freeze, I use the equation Q equals mH. Okay? Now, conventionally, there's no positive or negative sign here. I'm going to say negative Q because it's cooling or removing energy. And we should know that if I want things to freeze, I need to remove energy. So, Q is going to be equal to negative mH, right? I'm making Q negative. I'm making it negative because I will need to remove energy. So I just move the minus sign wherever. So that's equal to 340 grams times, if I want it to freeze, it's 334 joules for every gram. So 334 joules per gram. And if I do this math correctly, 340 times 334, that's equal to 113,560 joules. Okay? Negative. So this is my Q2. This is my Q1. This is my Q2. To freeze all that liquid, I needed to remove 113,560, or Q is equal to negative 113,560. And now, finally, I've frozen all of that liquid. I want to cool that solid now. Be careful. This is a solid here, right? I have frozen that liquid. Now I'm a solid. So let's be careful in this third part. What equation do I use if I'm changing the temperature? If I'm going from 0 to negative 12, I'm still going to use Q equals MC delta T. And my delta T is equal to negative 12, because I'm going from 0 to negative 12. So negative 12 minus 0 is negative 12 degrees Celsius. So my delta T is negative 12. I'm going to do Q equals, my mass is 340 grams. This is where we have to be careful now. And remember, why am I using the same mass and all these things? Conservation of matter. It's not going anywhere. Here's where we need to be careful. Are we a liquid anymore? No. I'm hoping you're saying no. Now we're a solid. Does a solid have the same heat capacity as a liquid does? If I scroll to the top, no. The heat capacity of solid water, which is going to be our pop or our soda, is 2.1 joules per grams degrees Celsius. So be careful. That's where you need to be careful in part 3 here. My C is 2.1 joules per grams degrees Celsius, and my delta T was negative 12 degrees Celsius. So if I do this math correctly, I'll do 340 times 2.1 times negative 12. And I get Q3 is equal to negative 8,568 joules. My grams cancels out with my grams. My degrees Celsius cancels out with my degrees Celsius. And now what do I do with these three Q values? Just like in the previous question, if I want the Q total removed, it's going to be equal to Q1 plus Q2 plus Q3. So on our unit test, you're going to have to be able to add up all the different energies to see what the total energy that's needed to be absorbed or removed. So I'll just do that. Negative 35,530 joules plus negative 113,560 joules plus negative 8,568 joules. If I do this math correctly on a calculator, I'll do negative 8,568 plus negative 113,560 plus negative 35,530. And I should get, according to this calculator, negative 157,658 joules. And if I want to have the correct number of significant figures, it looks like the lowest number of sig figs here is 2. So I can either round this to negative 160,000 joules, or with scientific notation, 1, 2, 3, 4, 5, it could be negative 1.6 times 10 to the 5th joule. And now if it acts for heat removed, you could say the total energy removed was 157,658 joules, or 160,000 joules, or 1.6 times 10 to the 5th joules. Notice how I don't use a minus sign over here. I don't use a minus sign over here because saying the word removed is like saying a minus sign.